Now we're gonna move on to another example. In this problem, we're gonna establish the shear and moment equations between point C and D of the cantilever beam. Now first, we'll label our points. This will be point A, the location of the support or the left end, and then this is point B because there is a concentrated load right here, and then this is point C, while this is point D. Now first, we're gonna solve the reactions at the fixed end. So since this is fixed, then we have three reactions. We have one vertical reaction, let's say that's AY, and then we have AX, and then we also have a moment reaction, which I will assume will be counterclockwise. So this is MA. Now summing up forces vertical, we can solve AY. So we have AY, which is assumed as upward, so AY, and then plus 40, because this is acting upward, so plus 40, and then we're gonna get the resultant of this triangular load. So the resultant will be acting at 1/3 of the base from the height of the triangle, and then the value of the resultant will be 1/2 the area of the triangle, which is 1/2 times base, which is 6 meters, times the height, which is 10 kN per m. And so m will cancel, and then we have 30 kN as our resultant. So we have minus 30 because this is acting downward. So this is equal to 0. Now solving AY, we can get negative 10 kN. Now since our result is negative, it means that our assumption is actually wrong. So since we have the wrong assumption, we're gonna change the direction. And so instead of upward, it's gonna be downward. And so let's just indicate that here. This is downward. And then for the purpose of simplification, let's just change the direction of AY. So this is gonna be downward. So downward. And the next, we will now try to solve the moment reaction at the fixed support. By the way, AX will just be 0 because we don't have any applied horizontal forces. Now to get MA, we can sum up moments about A. And so for point A, this doesn't have a moment arm, so it will not be included. And then by the way, this is 10 kN. However, we have an applied moment at A, which is MA, assumed as counterclockwise. So that's gonna be minus MA. And then we have 40 kN multiplied by the moment arm, which is 2 meters. And then that's gonna cause a counterclockwise rotation about this point. So we have minus 40 multiplied by 2. And then for this load, it will cause a clockwise rotation about this point. So this will be plus, and then the resultant load multiplied by the moment arm, which is gonna be this distance. Now we know that going to the height, this distance is gonna be 1/3 of the base. So 1/3 multiplied by 6, this is 2 meters. And so that means that this distance from this point up to here, that will be 4 meters. And then this total distance is 2 plus 3 meters, which is 5 meters. And so the moment arm of this load up to point A, that's gonna be 5 plus 4 meters. So times 5 plus 4, this is equal to 0. And so MA will be 190 kNm and then positive. However, the positive sign here doesn't mean that the moment reaction at A is clockwise. It just means that our assumption is correct. And so since we assumed counterclockwise and we got positive, then this is counterclockwise. So we have 190 kNm. Now again, we need to establish the shear and moment equations between point C and D. And so this is going to be segment CD. So we have segment CD. And so our cut is going to be just right before point D, which is right here. So this is going to be our cut. And then we have our shear equation. And then this should be in terms of X. Now for segment CD, let's try to identify our limits. Now segment C starts at 5 meters. So this is going to be, again, our origin of X is from the left. So this is going to be our X. And then it will extend to the cut, which is right here. So this is X. So we have our limits to be from 5. This is lesser than or equal to X, this value, and then X is lesser than 11. But again, we're not gonna put an equal sign for this one. Now for the shear equation, let's just directly write VCD. Now summing up forces up to this point, we have minus 10 because that's downward, and then plus 40 because this is acting upward, and then finally, we're gonna define the resultant of this triangular load as a function of X, this one. So in terms of the variable X. Now to make sense of that one, let's try to draw a triangle. Now let's say this triangle has a height of H and a base of B. Now if we're gonna cut the triangle, let's say along this line, and then this is our X. Notice that the height will vary because if this is our horizontal distance, then this is our Y. But if this is now our cut, the height is gonna be this one. So the height will increase according to the value of X. So it's directly proportional. And so that's why we need to define Y also as a function of X. So by the way, this is x. And then notice that for this cut, that portion, we have a resultant load of, let's say, 1/2 times x multiplied by y, the area of this cut. However, since we have two variables, x and y, we can't form the shear equation directly. Because for the shear equation, again, we need to define the shear in terms of the variable x alone. And so, sir, how are we going to define y in terms of x? Now, this is where ratio and proportion will come in. And so, by ratio and proportion, we can consider the whole triangle in which we have a height of h and a base of b. This is equal to y, which is the height of the smaller triangle, divided by the horizontal distance, which is x. And so multiplying this right here, we can define y. So y will be h over b multiplied by x. And so this is gonna be the height of the triangle. And so if this is r for the resultant load, then we have r is equal to 1/2 times x multiplied by y, which is h over b multiplied by x. Now h and b will depend on the height of the triangular load and its base. That's what you have to remember. But if you know the figure, you can just always redraw this. But once you will get the hang of it, you can just use this one directly. So we now have here, let's look at the base of the triangle in terms of x. We're not going to use this one. Let's first check the base of the triangle. Now for this triangle, the base would be this distance from here up to the cut. That's going to be the base. And so what is this distance in terms of x? It's going to be the whole distance minus 5 meters. So this is x minus 5. And so this is the base that we'll use for the value of x. And then for this base, we actually have this y from here up to here. That's gonna be y. And so by ratio and proportion, the height of the whole triangle is 10 kilonewton per meter. So 10 is to the base of the whole triangle is 6 meters. So we have 6. And then for this cut portion, the base is x minus 5 and the height is y. So we have y divided by x minus 5. And so multiplying this to the other side, we have y equal to, this is gonna cancel, this will become 5 and then this is 3. So we have y equal to 5/3 multiplied by x minus 5. So this is the value of y. Now for this cut, the resultant is gonna be the area, which is 1/2 times base times the height. However, since this is acting downward, this will be minus, so minus 1/2 times the base, which is x minus 5. Now here, we are using pointed brackets because what's inside cannot be a negative number. So this is 1/2 times the base multiplied by the height, which is 5/3 times x minus 5. So 5/3 times x minus 5. So we essentially just have this form where h is this value 10, b is 6 or the base of the triangle. But then this is where you have to be careful. Always check the distance in terms of x. And so that's why this is x minus 5. And so we now have our shear equation. Now we can simplify this further by expanding this one. So we have VCD equal to -10 plus 40. That's gonna give us +30. And then we can now join the constant terms. And then we're gonna join x minus 5 and also x minus 5. So minus 1/2 times 5/3. That's gonna give us 5/6. So 5/6. And then since we have two terms of x minus 5, then we can just join the two. This will now become x minus 5 and then squared. Now for the square of a binomial, we have a plus b quantity squared. Expanding this, we have a squared plus 2ab plus b squared. And so we're just gonna use this formula. Now our a is x and then our b is -5. So VCD equals 30 minus 5/6. And then we're gonna expand this one. So this is multiplied by a squared, so x squared, plus 2ab, so plus 2, multiplied by a, which is x, and then multiplied by b, which is -5. And then we have plus -5 quantity squared. So this will now become 30 minus 5/6 times x squared, -5 times 2, that's gonna be -10. And then multiplied by x plus -5 squared, that's gonna give us 25 positive. And so distributing 5/6, we will now get the following function. We have 30 minus 5/6 times x squared, and the -5/6 times -10x, that's gonna give us positive 25/3 multiplied by x. And the -5/6 times 25, that will be minus 125 divided by 6. And so joining the like terms, since these are constant numbers, let's treat the highest degree as our first term. So this is the highest degree, so minus 5/6 x squared plus 25/3 multiplied by x. And then 30 minus 125 over 6, that's gonna give us 55 over 6. So this will now be our shear equation. So this is VCD. Now we are already done with the shear equation. Now we're gonna form the moment equation. And so let's look at our triangle. Now considering this triangle, the moment arm going to y, that's gonna be 1/3 of x. So this distance is x over 3. Again, going to the height of the triangle, the distance from the centroid up to this point is 1/3 of the base. So this is our moment arm, x over 3. And so we will now form the moment equation, and then we'll still have the same limits. Now, a technique in forming the moment equation is you can just actually look at your shear equation and then just add their moment arms. However, for the moment equation, don't forget all the applied moment loads. This is where you have to be careful. And so for the moment equation of CD, we have MCD equal to, let's first include our reactive moment, which is 190 kNm acting counterclockwise. So that's going to be minus 190. And then we have AY, in which this was our force. So minus 10. Taking moments about this point, this is going to cause a counterclockwise rotation. So that's why this is still minus. Just try to look at the forces individually and then add their moment arms. Now the moment arm of the 10 kN load going to the cut, that's going to be X. So let's multiply this by X. And then now we have 40 kN acting upward. So that's going to be plus because it will cause a clockwise rotation about the cut. So 40 multiplied by this moment arm from here up to the cut. Now what is this distance? That distance will be X minus 2 meters. So we have X minus 2. So since the moment arm contains minus, we're gonna use pointed brackets. So we have X minus 2. By the way, you're also gonna use pointed brackets if any of the variable X inside our equations contains minus. For example, for this one, since we have X minus 5, we need to use pointed brackets. However, for the simplified shear equation, we're only gonna use the limits that we have set. So from 5 up to a point just before 11. And so I hope that's clear. Now, for the triangular load, this was actually our force. So we have minus 1/2 times X minus 5 times 5/3 multiplied by X minus 5. This came from 1/2 times X times Y, wherein this expression was our Y and this was our base X. And so this is our resultant force, and so we're gonna multiply this by the moment arm. Now the moment arm going to the cut is gonna be the base divided by 3, just like this one, X over 3. So we have, again, this is the force, and then our moment arm is X minus 5, the base, divided by 3. This is 1/3 of the base, just to reiterate. And so this is the moment arm. Now, to simplify this equation, we can first join the like terms. So this is a constant term, and also this one, and also this one, in which the value of this is 1/3. And then we can join X minus 5. This one, and this one. So MCD will be minus 190 minus 10X. And then distributing this one, we have plus 40X. And then minus 80. 40 times negative 2. And then we have 1/2 times 5/3 times 1/3. That's gonna give us 5 over 18. Now if we'll try to check, we have 1/2 times 5/3 times 1/3. We have this value. So minus 5 over 18. And then we're gonna join X minus 5. So we have 3 of them. So X minus 5 cubed. And so now we're gonna expand this term. If we'll cube a binomial, we have the following rule. A plus B cubed. This becomes A cubed plus 3A squared B plus 3AB squared plus B cubed. And so we're gonna apply this rule. By the way, for this term, our A is X and our B is negative 5. And so expanding this, we can join the like terms. So MCD equals negative 190 minus 80. That's gonna give us minus 270. Let's join the constant terms and also the terms containing X. So minus 270 and then plus 30X. And then we have minus 5 over 18. And then expanding this one, we have A cubed. That's gonna be X cubed. And then plus 3 times A squared, so 3 times X squared times B, which is negative 5, and then plus 3AB squared, so 3 times X times negative 5 quantity squared, and then plus negative 5 cubed for this term. So now we have, let's just move this, MCD equals minus 270 plus 30X minus 5 over 18, and then for this expression inside, that's gonna be X cubed, and then minus 15X squared, 3 times negative 5, that's gonna be minus 15 times X squared, and then plus negative 5 squared, that's gonna be 25. Multiplied by 3, we have 75. So 75x, and the negative 5 quantity cubed, that will be minus 125. And so distributing this, we can expand the terms. So MCD becomes minus 270 plus 30x, and then minus 5 over 18 x cubed, and the negative 5 over 18 times negative 15x squared, that's gonna be plus 25 over 6 times x squared. Let's just use our calculators. Minus 5 over 18 times negative 15, we have this one. And then times 75, positive 75, we have minus 125 over 6. So minus 125 over 6 multiplied by x. And the negative 5 over 18 times negative 125, that gives us 625 over 18. And then positive. And so we're gonna join the like terms. We have this one containing x, and also this one. And then we have two constant terms, minus 270 and 625 over 18. So we have MCD equal to, let's just order these by degree. We have minus 5 over 18 x cubed, and then plus 25 over 6 multiplied by x squared, plus 55 over 6 multiplied by x. If we'll join the two, 30 minus 125 over 6. And then finally we have minus 270 plus 625 over 18. Now we have minus 4235 divided by 18. So this is now our simplified moment equation. Now let's try to differentiate this function if we would actually get VCD. Now differentiating this one, we have negative 5 over 18 multiplied by 3 times x to the power of 3 minus 1, and then plus 25 over 6 multiplied by 2. Now again, we are just applying the power rule, and then times x squared minus 1 plus 55 over 6. This will be removed, and then the constant term will become 0. So we now have minus 5 over 6 times x squared plus, this will cancel, so 3, and then this is again 6. So plus 25 thirds times x, because this will become 1, and then plus 55 over 6. And so notice that this is the same with our shear equation. And so this is what I meant, that you can just form the moment equation and then just differentiate that to get your shear equation. Now that's to save time. Now notice that at point D, we don't have any concentrated loads or applied moments. And so this means that for x equals 6 plus 3 plus 2, that's going to be 11. So at x equals 11, since we don't have any applied loads, we can just use these equations, and then if we'll substitute 11, we must get 0. Because again, at the left end and the right end of the beam, our shear and moment values must start and end with 0. And so you can substitute 11 for this one or this one, so that you will be able to check. So at x equals 11, we may have this one for shear and this one for the moment. So this is VD, while this is MD. And then these values must be equal to 0 at x equals 11. So we have minus 5 over 6 times 11 squared, or you can just use x and then squared, plus 25 over 3 times x, and then plus 55 over 6. And so once you have done this, you can press calc and then input the value of x. So since we have 11, let's type in 11, press equals, we're gonna get 0. So this becomes 0. And then sir, why would it be helpful if we'll type x as a variable? Let's say you're asked the question, what is v at x equals 3 plus 2, 5. So let's say, what is the shear value at x equals 7 and at x equals 8? If you will not use the calc function, then you will have to individually type these. However, using the calc function, you can automatically get the value for x equals 7 and x equals 8. So press calc and then 7. You're gonna have this one, and then press calc again, and then press 8. So equals, you will have this value. So this is its importance. Now let's also look at the moment equation. So minus 5 over 18 times x cubed plus 25 over 6 x squared plus 55 over 6 times x minus 4235 over 18, press calc, and then 11, we're gonna get a value of 0. So this is for the purpose of checking. However, as early as this step, you need to check if you will be able to obtain a value of 0. So using this one, we have minus 10 plus 40 minus 1/2 times x minus 5 times 5/3 times x minus 5. Substituting 11, we have a value of 0. And then for MCD, we have minus 190 minus 10x plus 40 times x minus 2 minus 1/2 times x minus 5 times 5/3 times x minus 5 multiplied by x minus 5 over 3. Let's substitute 11, calc, and then 11, press equals, we're gonna get 0. And so to check if your equation is correct, always try to substitute a value every step of the way. So for this one, substitute a value, and then for your second layer of simplification, substitute the same value. If you're gonna get the same result, then your simplification process was correct. And so do that for every step so that you will be sure that once you get to the most simplified form, it's still gonna be the same with your original equation. Now that's another technique.